Okay. We're just going to look at harmonic motion here. In this section, it's all about harmonic motion, which is a form. It can be represented as a second-order differential equation of the form x double prime plus 2 times c times x prime plus omega squared, omega 0 squared, basically omega naught squared, is one way of representing that times x equals f of t. And we've seen this form before with the spring, especially. Even looked at it a little bit previously. But yeah, so 2 times c term is equal to r divided by L if it's an electrical circuit, or 2 times c is equal to mu over m if it's a spring mass system. And omega naught squared is equal to 1 divided by CL, electrical circuit, or k divided by m if it's a spring mass system. With those things being familiar, I believe, by this point to you. Omega naught equals natural frequency of oscillations, while f of t is the free term, and that's equal to e of t divided by L, e prime of t divided by L, depending on which type of electrical circuit we're looking at, what we want to know, if it's charge or current. Or f of t is equal to f external t divided by m, the familiar thing you should see by now if it's a spring mass system. But yeah, so electrical circuits and spring mass systems are the only things that really matter for this that we should worry about. But we're going to do more of a different thing mainly. Our biggest focus is on for just some weird graphing stuff, but we have a couple problems with these. But there is, because of how our solutions look. But in general, we have 3 different types we can have here. We can have unforced oscillations in this category, and that's when the free term equals 0, which means that undamped oscillations or damped oscillations. Those are both f of t equals 0, and that's what we look at in this section, is these 2 types. And then in another section or 2, you can look at forced oscillations where f of t does not equal 0. And undamped oscillations means c equals 0, so mu equals 0 or r equals 0. Like mu equals 0, you've seen that before, where damping is not present. So, and damped oscillations means c does not equal 0. That's the big difference. And furthermore, let's look at unforced undamped oscillations real quick. They have a general form. Because of c equals 0, we just have x double prime plus omega 0 squared times x equals 0. So lambda squared plus omega naught squared equals 0 is our characteristic equation. And we solve this, we get the square root of a negative. So it's plus or minus I times omega naught is the general form for this. And of course, with e to the 0, because a term is not 0, the equation will have a solution of c1 times cosine omega naught t plus c2 times sine omega naught t. This is the general for any case that fits in this category. And you'd solve for c1 and c2 based on initial conditions. The problem is that if you wanted to actually get a visual feel for this, which it's oscillation, so it's one topic that sometimes you want to look at the graph. So we can put in polar coordinates, and that can sometimes be making it it makes it a lot more easier to graph in many cases. Because you should technically be able to graph by hand if it's in a simple form, a cosine or sine function when it's amplitude and an angle. When it's in terms of amplitude and phase angle. But you can always use a graphing calculator usually if you allow one to double check and stuff. We're not going to get too much into this, but you can see briefly with some of these graphs, look at how it looks. No, it's old school algebra, and especially some trig ideas. But no, polar coordinates from calc. We have r times cosine of our angle, whatever symbol we call it, basically equals c1, and the sine one here equals c2. And then, and we also have r squared equals c1 squared plus c2 squared, and tangent of the angle equals c2 over c1. And we can convert we have x of t equals, so c1's r cosine. I'm just going to call it psi, I'm pretty sure it's like that. And c2 equals r sine psi, so we use those two, and we distribute out the r So it's cosine psi times cosine omega naught t plus sine psi sine omega naught t. And a rule of a trig formula gives us that the summation here will be this difference. It'll be r times cosine of omega naught t minus psi. And that's the simple formula, and you can technically graph this where r is amplitude on the graph. You have omega naught t and then minus an angle. But we'll do this with a graphing calculator mainly. It's a lot of, it can be better to see a proper graph since something drawn by hand no matter what. But here's the thing, the value of psi depends on quadrant when you're actually figuring this out. Because it's inverse tangent is used to solve for it. Because tangent psi equals C2, C1, so the inverse tangent of both sides psi will equal the inverse tangent of C2 divided by C1. So based on how we formulate, we have C1 on the x-axis and C2 on the y-axis. Because in our analogy, C1 is basically x and C2 is y. Like that's what they're based on in the formulas. Like you'd have r cosine of theta equals x and r cosine of theta equals y. So that's why it's like that. You know, notation. But basically the angle can go here. It can go like this in red. And just, it can go like that, it can go, or the angle can be smaller, like up here. Not angles, but basically there's 4 different situations, and 2 of them are special in how you solve for it. Basically the first and fourth quadrant are just inverse tangent of C2 over C1. The other 2, at least when you put them in the calculator, you have to make this correction. So you plug these into the calculators and you minus pi or add pi depending on which quadrant. Or you just keep it as is in the fourth quadrant. But and then I have some notes here like, oh, psi is between 0 and pi halves, so psi is greater than 0 for this. Then we have psi less than negative pi halves here in this quadrant. And negative pi halves less than psi less than 0 if it's in the fourth quadrant. But really, your C1 and C2 values are what you'll use to determine what quadrant it is. A positive C1 and positive C2, it's this one. Positive C2, negative C1, it's here. Negative C2, negative C1 here. Negative C2, positive C1 here. As long as you keep everything straight in this format, then you'll be fine. And real quick, unforced damped harmonic oscillating motion. We have 2 times C term here. C does not equal 0. So it becomes this characteristic equation, and you do it normal, and it has 3 cases. Not just the one. Like this only has the one case every time. So that's why it can always be converted into here, because it always follows the same basic format. So yeah, so if you're dealing with a case where it's just lambda, you know, it can be shown as lambda squared plus omega naught squared equals 0, then yeah, it's only one type of solution no matter what. Always going to be the complex numbers with that type of thing. You know, you can have complex numbers, you can have lambda 1 does not equal lambda 2, but they're real. And you can have lambda 1 equals lambda 2, real case. But that's unforced damped, and that can happen in all those different cases. So it's like, I could go into there's only one, it was one exercise that looks at it critically damped, which is when C equals omega naught. And there's overdamped and underdamped, which are based on C and omega naught. But we're not going to go into that right now, but you can always look in a book at that. Come up when it comes up. But they have terminology for it, and there's a, you know, like similar, you can look at the square root and stuff to determine and all that. So that was getting worked up. Here's one of the biggest focus. So we place the solution in the form y equals r times cosine omega naught t minus psi and graph it for these 6 exercises. We're going to use a graphing program because I try to draw 1 or 2 of them, and we're just going to graph. So y equals cosine of 2t plus sine of 2t. Very simple. Just c1 equals 2 and c2 equals 1 in general form of, and it's yt equals c1 times cosine omega naught t plus c2 times sine of omega naught t for comparison's sake. So r squared is equal to 1 plus 1, so r squared is equal to 2 basically. That's what it comes up to. So r equals square root of 2. And we can see omega naught equals 2. then we have to figure out our angle of phase. And it's quadrant 1 first because it's C1 and C2 are both positive. So psi just equals the arctangent of 1. It ends up, and that's pi force. And on a calculator, you can plug it in if you have it in radians. And it gives you an answer. You can basically put that into degrees and convert it back. Or you could just do it in degrees and convert to radian. Well, it's complicated, but just look at a unit circle and figure out what it should be. Like divide pi by something. That's not the point. The point is it's pi force. If you have your answer in radians, it'll be a decimal point. So you have to figure out exactly what that looks like. You can do trial and error real quick. But anyway, y equals square root of 2 times cosine 2t minus pi force. It's going to look like... And the main thing to note is, we'll show this in a graph real quick. It's going to look like that. I'll show it in real one where we can get points. So square root of 2. We have square root of 2 times cosine of 2x minus pi force. You can find these online. Whoop. Because this one is a little bit finicky like that when it wants. Not paying direct attention. And here's our graph, like starts at 0, 1. We go to pi 8 is a high amplitude. 1.414 is the square root of 2. That's why the amplitude especially is easy to figure on a graph like this. It's square root of 2 in this form. You can figure out how to graph it if you want to spend a little bit of time practicing graphing, looking up the tricks and stuff in this format. And the inside of the cosine is the phase figuring out. But no, these are sinusoidal functions as they're called, and they go on. And we start at where t equals 0. This program is x is t here. Plug it into this, but... And if we really want to, we could plug in, you get the same thing if you plug in cosine 2t plus cosine x. We'll sort out this time since that's not too hard to type in. As you can see, it went right on top of it. Same exact function. Only concerned about from 0 onward, t equals 0 onward, because we can't have negative time. So that's that. I got all these just... So y equals cosine of t minus sine t. This time we have c1 equals 1 and c2 equals negative 1. Omega naught equals 1. Just 1 times t here. So again, y equals square root of c1 squared plus c2 squared. This ends up just square root of 2 again. And we get c1 equals 1. So c1 is positive, c2 equals negative 1. So fourth quadrant. Again, just inverse tangent of c2 divided by c1. Give that up, but I wrote them down here in all the problems. So again, the quadrant 1, quadrant 4 are the same. It's the same procedure for psi. Well, you get negative pi force this time, of course, because it's inverse tangent of negative 1. It's negative pi force. So it becomes t minus negative pi force in our formula, and we plug it into that standard formula, and we get t plus pi force. So square root of 2 times cosine t plus pi force. You can see it's wider this time. Highest point is again the square root of 2, which is 1.414. Lowest point is well that negative version of that. Pi force is when it hits 0. Okay, well, I don't know why I put pi force here. It should be 1 instead, but but you can graph these, and that's you can use a graphing tool or calculator or whatever. Here we have cosine of 4t plus square root of 3 sine of 4t. Basically, these are you're just doing this for several times the same process. So 4 is omega naught, c1 equals 1, c2 equals square root of 3. Both positive, it's going to be quadrant 1. R equals just square root of 4, which is equal to 2. And then because square root of 3 squared is just 3, so 1 plus 3. Basically, you get R equals 2. Positive, positive, so quadrant 1. Psi equals inverse tangent of c2 over c1. An inverse tangent of square root of 3 is what this is, which is equal to pi thirds. So y equals 2 times cosine 4t minus pi thirds. Oops, skip. We don't need that. So you don't need the multiplication for this one. You can see differences though, no matter what was all these different ones. It's 2 cosine 4x minus pi, 4t minus pi thirds, just because I'm using x and units. In terms of time, 2 is its amplitude, and the width of the peaks basically is based on 4x minus pi thirds, the inside of the cosine. Uniform and all that. This is negative square root of 3 cosine 2t plus sine of 2t. So this time it's a little bit different to quadrants than what we're used to. Omega naught equals 2, c1 equals negative square root of 3, and c2 equals 1 from the bottom. You get r equals 2 again. So a negative c1 and a positive c2 means quadrant 2. So we have inverse tangent of c2 divided by c1 plus pi. We solve for inverse tangent first in terms of pi and then add by. So it's negative pi 6 plus pi, so this is negative pi 6 plus 6 pi over 6, so that's 6 pi minus pi over 6, so it's 5 pi over 6. So 5 pi 6. So 2 times cosine 2t minus 5 pi 6 is our answer. That's the solution in our form from this to that. So we have 2 times cosine 2t minus 5 by 6. And 2 is the amplitude again. You can tell things change, but there's not much to talk about here. But you can technically graph these by hand without a calculator. I've seen if you practice a while and look up all the techniques and tips on how to draw amplitude and angles. Amplitude is the basic part. It's this width that kind of takes time to look at and understand. I'm not getting into. So now we have a little bit more complicated. So we have 2.5 for omega naught, 0.2 for C1 and C2 equals negative 0.1. We get R equals 0.2236. We have positive C1, negative C2, so quadrant 4, just the octan of them. We get negative 0.4636, so it's a little bit ugly, but again, this form. We enter this in very carefully. But no, there is no, the reason why we don't have it in terms of pi is because there is no exact pi analog for this. Six, 3, 6. Oops. We have 2.5x plus 0.464636. And the graph, we're going to zoom in a little just so we can see it. Yeah, 0.224 and negative 0.224, so the amplitude is those. This is 0.224 is our amplitude. Yeah, there's nothing too mark plugs up, but this is a smaller graph, and then because of our small values of C1 and C2. Are very low. Anyway, let's not get distracted with this. We have another one with decimal answers. So y equals 0.2 cosine 6.3t minus 0.5 sine of 6.3t. So 6.3 is our omega naught. C1 equals 0.2, C2 equals negative 0.5. Again, quadrant 4 because we have a positive C1, negative C2. Same type of arctangent stuff. R becomes equal to the square root of 0.29, which is equal to 0.5385. And when you put this into a calculator, you get arctangent negative 2.5, so that's equal to negative 1.1903. So, let's start here. Five, 3, 8, 5. So 5, 3, 8, 5. 5, 3, 8, 5. 6.3. So 6.3 plus 1.19. .1903. Yep, 538 is our amplitude. But that's all there is to this type of sinus graphing. But you can technically graph this by hand if you really wanted to. It's just not going to be pretty at all, potentially, unless you have a very delicate hand. Note this type of graph in the last one is kind of more messy than anything. The other ones I could see actually looking decent by hand, especially if you look up how to do them properly. Now it's time for a couple word problems. Just get rid of that because it'll be a lot easier. So we have 0.2 kilogram mass attached to a spring having a spring constant 5 kilograms per second squared. The system is displaced 0.5 meters from its equilibrium position and released from rest. If there is no damping present, find the amplitude, frequency, and phase of the resulting motion. Plot the solution. So we've looked at this before, this formula in red here. And it's the same. We have mu equals 0 because there's no damping. We have 0.2 kilograms. Mass, K equals 5 kilograms per second squared. Oh, and F external T equals 0 since there's no mention of it. So we plug that in, we get y double prime plus 25 times y equals 0. And this is equivalent to y double prime plus omega naught squared times y equals 0. So omega naught squared equals 25 implies omega naught equals square root of 25, which is equal to 5. Just so you'll see that as you take the square root of this negative 25, you get plus or minus 5i. So we get yt eventually. So we solve it basically after plugging in this information. We get c1 times cosine 5t plus c2 times sine of 5t as our solution. We're finding amplitude, frequency, and phase of the resulting motion. Plot the solution. So we're going to have to convert it. But first we have to find C1 and C2. It's displaced 0.5 meters, that means y of 0 equals 0.5. Released from rest means that velocity initially is 0, so y prime of 0 equals 0. We can solve for C1 easily. Y of 0 equals C1 times cosine of 0 plus C2 sine of 0 equal to 0.5. So it's C1 times 1 plus 0 equals 0.5, so C1 just equals 0.5. It's C1 plus 0 equals 0.5, so 0 plus something is the same as what that thing is. So that's C1. Now C2 we need to take the derivative first before we can find it. So y prime of t is just you take out negative 5. Derivative of cosine is sine, is negative sine, times whatever's inside of its derivative, and sine is the same way, but it's positive cosine. So negative 5c1 sine of 5t plus 5 times c2 times cosine 5t. Y prime of 0 equals 0, which is equal to this saying sine of 0 is 0, so it just becomes 0 equals 0 plus 5 times c2. Cosine of 0 is 1. Cosine of 0 is 1. So c2 eventually just equals 0. So this actually simplifies very easily. Y of t equals 0.5 times cosine 5t plus 0 times sine of 5t. It just becomes 0.5 times cosine of 5t. This is an interesting one, I think, because you technically don't have to do any rough handling of it like before. The trig trick or two, use the pull and all that to get in this format. It already defaults to it. Since it is undamped, unforced oscillations, we could look at yt equals r times cosine omega naught t minus psi solution form. And we'll check them, but you see, we could have just entered it like that since we knew that. You could technically just skip it in some cases, at least when you're doing it for yourself and not showing it. You could just skip ahead and be like, oh, let's just do that. But here, we don't even have to. It's already in this form by default. We have r, we have omega naught, and we have an angle of 0. But you see, you end up with just the square root of 0.5 squared, which is 0.5 and then, as already shown, you have C1 equals 0.5, C2 equals 0. So let's assume that's in the first quadrant since they're both, well, you get inverse tangent of 0, which is going to be equal to 0. So it is by default in this form due to C2. So C2 equals 0 kind of allows this to happen, was how it's all set up. But now, real quick, the amplitude equals r in our notation, which is equal to 0.5 meters. Phase equals psi, which is equal to 0 radians. You don't have to follow because it's just 0. It's 0. Anything is 0 for a unit. Frequency is equal to omega naught, which is equal to 5. If we want to put a unit to it, it's inverse seconds in this type of problem. Because of it. But now that that's done with, yeah, it'd be in reciprocal seconds because kilograms per second squared divided by kilograms is just seconds to the negative second power. Take square root, that'll be seconds to the negative 1 power. But anyway, that's not worrying about it. That's just what you'd get for the three things, and we can graph it. So here we have a simple 0.5 cosine of 5t. It makes sense. It's a very simple equation, but 0.5 is the amplitude. So you see that it oscillates between 0.5 and negative 0.5. Then just 5x. It's 1, 2, 3, 4, 5. It goes through several peaks before it gets to that 5. Yeah, it's pretty... We go into quite a few peaks in short periods of time and all that. But regardless, let's just look at the graph. So now 18, we have a similar problem, but this time we have damping. 50 gram mass, so we're going to have to convert that to kilograms. You always work in standard units. Kilogram is standard for mass, meter is standard for lengths and all that, and etc. Seconds, everything. So it's 50 gram mass stretches of spring 20 centimeters. Find a damping constant mu so that the system is critically damped if the mass is displaced 15 centimeters from its equilibrium position and released from rest. Find the position of the mass as a function of time and plot the solution. Same equation as before. We've looked at that before, so I'm not going to... Oh yeah, we also looked at it before. We knew K equals mg divided by x star. X star is the equilibrium position. How far it's stretched basically naturally, which is given as 20 centimeters here. Which you divide by 100, it's just 0.2 meters. G always equals 9.81 meters per second squared. Mass is equal to 50 grams divided by 1,000 grams per 1 kilogram, so we get 0.05 kilograms. So you can solve for K with that in our standard units. That's the first step to solve for K. We got K equals mg divided by x star from our previous work in the past. Go back on section, I think 4.1, 2 videos ago basically on that. That's where you get that K equals mg divided by x star. It's from some of the work involved in formulating an equilibrium position and all that. And formulating this general formula. But aside from that, we do plug those values in and we get just 2.4525 kilograms per second squared. We have K, we have M, and we have mu. Well, we have to solve for mu. But with how I did it here, well, F external T equals 0, of course. There's no, I think a motor is one of the types of things where it can be having a motor attached to it as a spring. It'll further affect the oscillations, but that's a future thing if we get to that. No, but we can plug in everything except for mu because we'll solve that in a little bit. For critically damped case but the critically damped case means C equals mu 0. Omega naught. C equals omega naught. But no, let's put in this formula. So y double prime plus mu divided by 0.05 kilograms times y prime plus this stuff times y equals 0. So we have 20 reciprocal kilograms times mu times y prime, and that. So omega naught is equal to square root of km, as we established at the beginning. That's in the standard formula here. It's written in that. So the square root of 49.05. So omega naught is equal to 7.004. Oh yeah, omega is the W symbol. I hope I specified earlier, but yeah, it's omega. It's a lowercase omega. So 2 times C is equal to mu divided by m. So C equals mu divided by 2m. And C also equals omega naught, which is 7.004. Plug that all in. We eventually get mu equal to 0. We can round a little bit, so it's 0.7 kilograms seconds to negative 1 power. So mu is equal to 0.7 kilograms a second. That's our critically damped value of mu. Oh, we can plug it in, so, and we round, eventually we go, so we have 14y prime plus 4, so round 49.05 to 49, because it makes it nice. So y dou prime plus 14y prime plus 49y equals 0. You do characteristic equation, we can easily separate this into lambda plus 7 times lambda plus 7 equals 0. So lambda 1 equals negative 7 equal to lambda 2. Yep, we solved this. Because it's, so the fundamental set of solutions is e to negative 7t and t times e to negative 7t. To this model question. Like before, this is in a case when we have two real values that are equal for lambda. So just the sum of these with the constants added in. And y prime of t is this. You can read it off here. Y of 0 equals negative 0.15 and y prime of 0 equals 0. Because it's released from rest, so velocity will be 0 initially. And it's displaced 15 centimeters from equilibrium, so negative 0.15. E to 0 is 1, so that's one point. Anything times 0 is 0, so of course this can't. So we just get C1 plus 0 equals 0.15, or negative 0.15. And 0 equals negative 7 times C1 plus C2 minus 0. That's what the symbol is down to. So C1 is equal to negative 0.15, C2 equals 7 times, because we add negative 7, we add negative 7 C1 to both sides to get, we had some, whatever, we simplify down. So all I do is plug that in. So 7 times negative 0.15 will be our C2, so C1 equals negative 0.15, C2 equals negative 1.05. Those are our things, so solution is yt equals negative 0.15 e to negative 7t minus 1.05 times e to negative 7t times t. We can divide out negative, then also we can simplify out e to negative 7t to get negative 0.15 plus 1.05t all times e to the negative 7t. And this is like supposedly the best way to graph it, but we're not going to worry about graphing that by hand at all. So let's look at this. Negative. We have negative 0.15 plus 1.05x. On parentheses. Then we have e to the negative 7t multiplied by it. Hey, let's zoom in. Because this is a tragic situation it ends up as. With these values, the critically damped case does not last long. It's because it's only displaced. It's 15 centimeters, and we're talking about small measurements here. That's probably. But zooming in a little bit. So that's 0.2. So it never gets so. It decays. And this is sort of a common thing with these types of problems, is that there's going to be some kind of decay involved, generally speaking. I think that's one way of saying it. The functional decay was time until it reached 0 eventually. It's basically, see, it's going, it almost hits, it hits basically 0 as far as it's concerned already at 1 point something. But that's what you get. Damping does that, so. So we have a final one. We have one electrical circuit, and it's a little bit long. Okay, we have 0.008 farad measured capacitor charged to 50 volts and then connected in series with an inductor, 4 Henry, and a resistor, 20 ohms. Yeah, 20 omega, the large uppercase omega. So initially there is no current in the circuit. So I of 0 equals 0. Find the amplitude, frequency, and phase of the current and plot the graph. So we're going to have one initial condition, and we're going to have to do some tricks. And I think this problem's a nice look at that to see all the stuff that goes on. So we have general form of harmonic motion here. This is going to be a damped case, basically. But it's not plugged into an EMT, saying an EMF signal is not given. It's not plugged in. It's not plugged into a continuous source, so no thing there. So we're going to have f of t equals 0, basically. Basically, the free term will be 0 because E of t will be 0, or E prime of t goes in also. You'll see. We've seen previously that, we should, in the class work at some point, we have I prime plus 1 divided by CL times Q plus R divided by L times Q prime equals E of t divided by L. And we also know I equals Q prime. So there's a relationship between charge and current in the equations. So we can plug in Q prime here, where I is, and we get Q prime prime, so it's Q double prime plus R divided by L times Q prime plus 1 divided by CL times Q equals E of t divided by L, and that's a differential equation that we could solve. Oh, I see two, we want one. Okay, well, I'll explain it. So, but yeah, we plug that in, we get our equation that we're going to look at. We're going to look at charge instead of current for a while. So from that, we'll get our current equation. So derivative was, but real quick, an overview of this. So we take the derivative of this function with respect to time, and we get Q triple prime, Q double prime, and Q prime. And then we use I equals Q prime, and get I double prime, I prime, and I. So that's our equation for current, which we could do. We could use this if we had two initial conditions. We want I at t but need two initial conditions. With Q at t we have two initial conditions, as we'll be seeing shortly. So basically, yeah. Q at t we technically have two initial conditions, even though it appears like we have none. It's interesting, but they gave us enough stuff to figure out two initial conditions for Q, though. But yeah, so this should be 1. 1 becomes, with this information, E at t equals 0, C equals 0.008 farad, L equals 4 Henry, R equals 20 omega, 20 ohms, I mean. So you plug them in and then simplify down. You get Q double prime plus 5 times Q prime plus 31.25 times Q equals 0. And that's a simple enough equation to solve. So we have a characteristic equation with lambda values put in, and then we solve. We use the quadratic formula. We get a square root of a negative number, square root of negative 100, so that's plus or minus 10i. So, and then we divide by 2 both things, so it's negative 5 halves plus or minus 5i. So we have negative 5 halves plus 5i and negative 5 halves minus 5i for a value of negative 5 halves, b value of 5. So it's e to the at cosine bt, e to the at sine bt are things. So that's why it's plugged in blue here. Fundamental solution. So q at t is equal to this. We distribute out e to the negative 5 halves t, which is in common with our stem, to simplify down. And that's so when we take the derivative, it works out, which we'll have to take when we're solving this. So here's the initial conditions. Q of 0 equals C times V. So the voltage given, which is 50 volts, and capacitance, 0.008 F. The product of those gives us our initial current, or our initial charge. So Q of 0. So it's 0.4 coulombs. And we know that current equals Q prime, and we know initial current, I of 0, is equal to 0. That's given. That means Q prime of 0 equals I of 0, which is equal to 0. So Q prime of 0 equals 0. And that's how we trick everything. We end up with this trick, and we can solve this, and then eventually, using all this, we'll get... So initial conditions here laid out. And Q prime of t, we solve it. I put it in this format here, so we can easily solve it. So it's a product rule. This can be solved, we can take derivative of that times this, and then derivative of this times that. So distribute negative 5 halves times e to negative 5 halves t times this unchanged, plus e to negative 5 halves t times, well, you take negative 5, so it's negative 5 times c1 times sine of 5t plus 5 times c2 times cosine of 5t. And due to I at t equals Q prime of t, we have formula for current. We just need values of C1 and C2. So yeah, so this Q prime of t is also equal to I at t. So we got our current formula and can graph it once we solve for C1 and C2. But yeah, that's all you have to do here. And just real quick, was this all electrical circuits? I've warned you, E at t, L, or E prime at t, L is our F at t in these equations. We're going any further, but yeah, omega naught squared equals 1 divided by CL, which you saw here. 1 divided by CL, R divided by L is 2 times C. See? Same format. But anyway, so as we were saying, we have our Q prime and our Q, so we can solve for C1 and C2. Cosine of 0 is 1, sine of 0 is 0. We'll them in. Plug in 0 for all these, and we're going to see things simplified out. So it becomes 0.4, and e to the 0 equals 1. So 0.4 equals C1 plus 0. 0 equals negative 5 halves times C1 plus 0 plus negative 5 times C1 times 0 plus 5 times C2. It becomes C1 equals 0.4, and 0 equals negative 5 halves C1 plus 5 times C2. Add 5 halves C1 at both sides, and we divide by 5. We get C1 equals 0.4, and C2 equals 1 half C1. So C2 equals 0.4 divided by 2, basically, which is equal to 0.2. And we can change this in the format of 2/5 and 1/5. And we do this for when we simplify further. And we plug them in like this. We plug in the Q prime at t instead of Q at t, because there's no point in taking derivative of that again. We want I at t. We don't care about Q at t. So Q prime at t equals I at t. And when we plug it all in, and we have to distribute in here, and we cancel out a couple terms. We combine like terms in the end and simplify. After distributing this in, we can combine them. So the cosine terms both cancel out, and the sine terms can be merged. So it's negative 1 half minus 2 times e to the negative 5 halves t times sine of 5t. Then in the end, it's I at t equals negative 5 halves, because negative 1 half minus 2 is just negative 5 halves, times e to the negative 5 halves t. Got cut off a little bit. That's 5 halves t times sine of 5t. So And we can convert this into cosine terms by we switch to amplitude value and make it cosine. 5t, we add to that term, we add pi halves, and we switch to amplitude value. The value of it. So from negative to positive in this case. Everything else can stay the same. So amplitude equals 5 halves, and these two things have the same exact graph you want to see, but we're not going to worry about that. You can graph it yourself. Amplitude equals 5 half. It decays over time, but that's when it varies. Invariably will go to 0 eventually. Like you won't have anything fluctuate. Phase equals negative pi halves because it's omega naught t minus phase angle, so negative pi halves, and frequency equals omega naught equals 5. Now omega value you could see early on. I guess you couldn't here. Well, you kind of could, but yeah, you could, I guess, kind of, but yeah, we graphed this one, 5 halves. Negative 5 divided by 2. Zoom out a little bit, so it has a little bit of a jump. Well, not much. So it goes down. Five half times e to negative 5 halves t times cosine 5t plus pi halves. Yeah, it goes down and up a lot less, and eventually down again. As you can see, it's eventually just going to 0 eventually. As the previous two sort of did. Well, the previous one, I mean. At least. That's what that exponential term that's negative, it inevitably will end up with. Because e to the negative infinity is 0 as you pick the limit of t approaches infinity of e to the negative t or any type of similar to that, or negative 5t or whatever, will become 0 eventually. And 0 times other things will equal 0. You can see it's all in the product. So the behavior makes sense as that goes. So I really don't like calling it the amplitude because 5 halves. I guess if you wanted to call it, could be the whole thing, but sometimes they want to call it. Sometimes they want to just call it 5 halves. I mean, they won't even say it, but you probably wouldn't be asked for amplitude anyway in a case like this too much. Because it's a strange case like this. It is kind of cool. But usually with graphs, the more concerned with the first one where it's undamped. And that's it for that section.